Okay, let's now start looking at ways to improve our single cycle architecture. And the way we're going to do it is by pipelining. Now, I don't know if that word means anything to you right now, but I hope by the end of this course it's going to mean a great deal to you. Pipelined architectures are the current approach to modern processor performance. So what we're going to do is we're going to start fetching and decoding and even executing the next instruction before the current instruction is finished. So before, what we had was do all of an instruction. When you're done, are you completely done? Yes. Now start the next one. And so we only ever had one instruction in process at the same time. That would be like sending a drop of water down a pipe and saying, did it come out the other end? Okay, now send the next drop, okay? Not using the pipe very well, is it? But how do water pipes really work? You push in water continuously, and water comes out continuously out the other end. We're going to do the same thing with instructions. We're going to use our hardware continually, pushing instructions in before the first one's finished. We'll be pushing in the second one, and the third one, and the fourth one, and they'll all be moving through our data path in a form of parallelism. They're not all at the same place at the same time. The one that went in first will come out first. The one that went in second will come out second. But you see that for every instruction, need to fetch. And as we fetched it, we start to decode it. That means we don't do any more fetching until the next instruction comes. Well, why wait until the instruction writes back its results before you fetch the next instruction? We could fetch the second instruction as soon as we finish fetching the first instruction. Now that means the second instruction is being fetched and the first one's being decoded. And after it's being decoded and the register values have been gotten out of the register file, then the first instruction moves into the ALU and we do something. The second instruction can move into being decoded and its values from register file fetched. That means we're not fetching anybody with the instruction memory anymore. We could put the third instruction and fetch that from the instruction memory. So we've got fetch, decode, execute, which is the ALU doing some operation. Those could clearly be pipelined. Well, that's what we're going to do. Remember what we've got. The performance equation says CPI times clock cycle time times the instruction count. If we keep CPI 1 but make a much shorter clock cycle time, we're going to get a big gain in performance. And that's what we're going to do. With ideal conditions, pipelining allows us to have a very large speed up. With a large number of instructions, the speed up from pipelining is approximately equal to the number of stages in the pipe. So if you have a 5-stage pipeline, as I'm going to show, we're going to have a speed up factor of 5. In other words, this stays 1, and this becomes 1/5 of what it was before. Okay? Now, fetching and executing more than one instruction at once is going to require us to have some coordination, and we can actually get into what's called superscalar processing, and we'll get to that just a little bit later. First, let's do simple pipelines, then we'll start to fetch and execute more than one at once. Right now, we're going to fetch one at one time. We're going to execute one at one time. All right, let's continue with this idea about what we would do in a cycle. If our cycles were short, they would just be enough time maybe to go to the instruction memory and get the instruction out. And maybe there would be just enough time to take that instruction and decode it in the control units and get its register values out of register file. And maybe it would be just enough time to send its inputs to the ALU and get the output from the ALU. And maybe it would be just enough time to send the output from the ALU to data memory and do the data memory operation. And maybe just enough time from the data memory result to get it back into the register file. So for example, load word, as you remember, fetched, then got its register values while it was decoding, then used the ALU to create the address, then went to data memory and got out the value that was being read, and then wrote that back into the into the register file. So we call this fetch, decode, execute, memory, and write back, because we're writing the result back into the place that it will be stored. So those 5 stages are the worst case. Remember, we looked at other instructions, and store is only this many, and the ALU instructions are this plus that. The R-type uses those and those. Branch only uses the first 3. Jump only uses the first 1. So this is the worst case. But you can see that the cycles now are very short. It's not a long cycle to get all that done. It's a much shorter cycle. That means our clock rate is much higher now with a pipeline. Much higher clock rate with a pipeline. So this just says what the stages do. Are there any questions about what the load word instruction has to do? I think we went over it pretty carefully, but we got to do that in 5 parts. And you can see we're going to have a clock that's going to end right there and begin a new operation there. So it's like 5 separate operations. And as soon as I've fetched load word and cycle 1 is done, and the load word is now being decoded, I could fetch something else with the same instruction memory. And that's what I'm going to do. Look at the pipelining. See what we do? We overlap the execution of the operation. So if this is a load word, followed by a store word, followed by an R type, we fetch, decode, execute, do memory, and write back. And as soon as fetch is free, we can fetch a different instruction. The next one, the store word, fetch, decode, execute, memory. We don't really need a write back, but just for completeness sake. And then for R type, fetch, decode, execute, we don't really need a memory. But if we move this right back to here, then it's going to conflict. You can see that we have a 5-stage pipeline, and this is going to improve our throughput tremendously. Before, we finished 1 instruction per long clock cycle. Now we're going to finish 1 instruction per short clock cycle. And since there's 4 or 5 short clock cycles per long clock cycle, you can say that now my throughput is much greater. In other words, how many finished instructions am I catching per unit of time coming out of the end of the pipeline? A lot. 4 or 5 times as many as in the previous model. However, latency, which is how long does it take to finish 1 instruction, hardly changes at all. Look at this. Is this any shorter or any longer than it was before? Not the same. Actually, a little bit longer. Because 200 and 100 and 200 and 200 and 100 added up to 800, but now it has to be 200, 200, 200, 200, and 200 because I can't have varying clocks. So the clock has to stay fixed at 200, and therefore I have a 200 picosecond clock for what only needs to be a 100 picosecond access to register file. So it actually now takes 5 cycles of 200 picoseconds, grand total 1,000 picoseconds. Before, when it was a single long cycle, it was an 800 picosecond. But let's ask the question. In 800 picoseconds, how many of the old kind of instructions did I finish? 1. In 800 picoseconds, how many of the new, in 800 picoseconds, how many pipeline instructions do I finish? 800's 4 of these. 4 of them are dropping off the end. There's 1 coming out every clock cycle. So I'll finish 4 in the same amount of time that I used to finish 1. So I have a speed up of 4. Well, wait a minute. There's 5 stages. How come I don't get a speed up of 5? And we've already answered the question. Because 2 of these stages use the clock less than 100%. Okay, so there's a slight inefficiency with this. How could I make it better? How could I have my pipe be optimal? And the answer to that is have every stage need exactly as long as the clock cycle. Or chop up the work in exactly equal sized pieces so no stage says, well, I'm done, I have some tea drinking time. If there's tea drinking time, it means your hardware is not being used to do useful computation. Okay. All right. So just as we had before, look at this. Read the bottom there. Clock cycle is determined by the slowest stage. Before it said determined by slowest instruction. Now it says determined by slowest stage. And some stages don't need the whole clock cycle. If you give them tea drinking time, you're not going to have maximum efficiency. And for some instructions, some stages are wasted. Look. And those guys don't really need a write back on store word. Don't really need a memory access stage on R type. Okay? So nothing's going to be done during that cycle. But in order to have 1 instruction coming out of the end of the pipe every clock cycle, we need to stagger them in this diagonal approach. Okay. So here's a comparison of single cycle and clock cycle. In single cycle, our clock was 800 picoseconds. We already calculated that out. So therefore, in 1600 picoseconds, as you see, I get 2 instructions done with some waste. On the other hand, if I pipeline and do a load word, a store word, and R type, as you can see, they start falling out every 200 picoseconds. I get a finished instruction every 200 picoseconds. So question, how long does it take to complete 1 million adds? How long does it take to complete 1 million adds? Take the top. In single cycle, how long does it take to do 1 million instructions? 1 million times 800, right? 800 million picoseconds. Okay, let's come to the bottom. How long does it take to do 1 million adds? In other words, this, you know, 1 million R-types, all lined up like that. Well, it takes the time to fill up the pipeline and get the first one to the end where it's ready to come off, and that's the first one. And then you do that 1 million times in a row, and how many cycles does it take to get an output from our pipeline? 200. So it's 200 times 1 million plus 4 more to get the thing filled up. Yeah, so the fill time or the flush time at the end to clear it out is negligible if you do a lot of instructions. So therefore, speed up is, instead of 800 times 1 million, is 200 times 1 million, speed up of 4. Much, much more efficient. Can you see why? Right at this time, my memory's being used, my ALU's being used, my register files being used. They're all being used to do useful work, but on different instructions. My memory's working on the load word, my ALU's working on the store word, my register file and control unit is working on my R-type. They're all doing useful things. It's not, hey, everybody drink tea while he works. Have you ever seen any construction projects where everybody just kind of sits around and one poor guy with a shovel is digging and everybody says, hey, kolla gelsen. I've seen lots of those. It's not very efficient, is it? All that manpower is just observing and the hole is being dug very slowly. It would be a lot better if they all had shovels and dug. What we're doing here is putting everybody to work. Putting everybody to work in the pipeline. So all our hardware is busy computing for us, so we should get a gain in performance. Okay, so now let's talk about how to pipeline the MIPS ISA, how to design a pipelined architecture for our MIPS processor. Okay, what makes it easy is the following aspects of our RISC approach to designing an ISA. All instructions are the same length. We don't have varying length instructions. We can always fetch in the first stage, and we can decode in the second stage because we know that there's not more to fetch. So you got it all on the first stage, you can start decoding it in the second stage. There's only a few instruction formats. In fact, there's only 3 formats. And there's a strong symmetry of those. Remember, opcode is always in the same position in every single one. The 16 bits at the end match up the 16 bits in the last 3 fields of R-type and I-type. The RS and RT fields are in the same place in the RS and the I-type. There's a strong symmetry. Okay? We only allow memory to be done in loads and stores. We never allow any memory operations to be done on operands in memory. That makes it very easy. That allows us to use the execute stage to calculate the memory addresses because the execute stage isn't being used to actually add things from memory. So that helps us. Each instruction writes at most 1 result. We don't allow changes in multiple things in a single cycle. And it affects the last few pipeline stages. The mem stage could have a write to memory, or the write back stage have a write to register file, but it's at the end. We don't have early writes, we have late writes. That also helps the pipeline. And finally, the operands must be aligned in memory. We don't allow our operands to be all over the place in memory, so a single data transfer takes only 1 memory address. But if you have unaligned memory operands or memory values, you have to get part of it and then you have to get the other part of it because it's not lined up on a boundary. But this way, a single memory load can bring in the whole data operand. Okay, now, have a look at this and what's in blue. IF says this is the part that does the fetching. ID says this is the part that does the decoding. EX says this is the part that does the executing. MEM says this is the part that does the memory access. And WB says this is the part that writes it back. Okay? And what we've done is, because it used to take a long time to get everything done, we've chopped it up with these pipeline registers and just said, please, in one very short clock, take this and get it done and get it into there. Because, oh my goodness, we're going to have a high-speed clock. We just barely have time to get that much work done. Of course, if you want to do that much work, it's going to take longer. The amount of combinational delay is much longer, therefore I need a much longer clock cycle. But if I chop that combinational delay into pieces and just take sections of it, then this doesn't take so long. And this doesn't take so long. And this doesn't take so long. So all I have to do is get from here to here. So you might say that I've got partially computed results as I move along the pipeline, and when they're finally computed, then they can be written back to here or written back to here. Partially computed results need to be held in a storage register. And that's why you see the extra storage registers. Those are our pipeline registers. I've got a pipeline register here called the IF-ID register. Can you see where the name came from? It's on the boundary between the instruction fetch stage and the instruction decode stage. So it's the IF-ID pipeline register. Here's one on the boundary between the decode and the execute stage. So it's the IDEX pipeline register. Okay? We got it? So we're putting in these registers and giving them all, as you see here, a common system clock. So everything begins with the PC. We get the instruction into here. Next clock cycle, that was called fetch. Next clock cycle, those things cause our source operands to be found, and the instruction is now decoded. We haven't got the control on here yet. The next is the execute. Send those in here and get a result here. We've executed. Next one, if we do it, is memory. Notice you can skip around. You don't have to have a memory stage, but if you do it, you go through memory and get something here. And the last stage is choose which one you want and make sure to get it back and have it written into here. Okay? All right, now that's probably something you never saw before. Pipeline registers. Chopping up a long sequential combinational data path into pieces in order to speed it up and have a higher clock is probably something you never saw before. We didn't do this in CS-224, but now we're doing it now. So I'm moving up your digital design to the next highest level. Is this something that only is done in computers? No. Pipelining a long delay chain in order to have a higher clock speed and to get results more quickly is a common digital design technique. All you do is you add these registers. It's kind of like slicing a loaf of bread. You know, the loaf of bread is the hardware in black. We're just slicing it at places, and we hope our slices are about equal in thickness so that they'll fit in the toaster. No, so that they'll have the same clock delay. Okay? That's what we're trying to do here. All right, are there questions about this? This is pretty profound. This first pipeline architecture you've ever seen, I guess. And this is, right now, king of the hill. Okay? This approach to parallelism gives us tremendous speed up. And so this is the modern architectural approach. And so we want everyone to understand. It's not like optional, oh, that's hard, but he's not going to really stay on it. This is where we're going the rest of the course. And you're actually going to design a pipeline processor in Project 2. Yes?
Are these registers in the 32 registers that we use? Or
No, the 32 registers we use are in here.
okay.
So these are external registers.
External.
Yeah, external registers, yeah. And 32 registers also didn't include this one either. Remember, we already had a PC. Now we just have some more. Yes?
I get confused about the branch instruction. As you know, branch instructions sets new address, and in this slide we fetch the fourth clock cycle.
Yeah. Yep.
How it's now?
Okay, he's asking about branch instruction, and he might as well ask about jump as well. What's shown here doesn't include the instructions which change control. We're going to have to add them later. It's a little bit different. So right now we're just looking at data processing instructions. Okay, so this is your R type and some of your I types, but not the branches and not the jumps. So I'm going to have to hold that question. Anybody else have any comments or questions about our pipelined architecture here? Yes.
I have a little one.
Yeah,
Before the
sure.
last multiplexer, why did we add it before the memory?
Yeah, yeah. Okay, his question is this. Look, what is the purpose of this pipeline register? For Pete's sakes, if it's coming out of here, and all it has to do is get through this multiplexer and back into here, why are we chopping it and saying, Yeter, Arctic, that's enough work for today, come back tomorrow and we'll finish the job? That's your question, isn't it? Yeah. He says, look, we got it out of here, the çok az kaldı. Evet, gitmeye. Ya tamam, anlıyorum musun? Şurada. So why do you save it here and say, wait one more clock cycle? And the answer is, surprisingly, because this was one of our larger delays. If you remember, the memory access here and here, we expected that's about 200 picoseconds. We're stretching our clock just to be for that. And so now, if you say, oh, do that, and do that, and do that, remember the write time here was 100. Oh, now our clock cycle went to 300 plus mux delay. So we don't want to do that. We want to keep our clock cycle as small as we can. And remember what we said was, we want to slice the pieces of bread equal thickness. The reason pipeline architectures lose performance is with unequal delay. We already said, if that's 200 and that's 100 and that's 200 and that's 200 and writing back here is to 100, Malisev, we have to have a 5-cycle grand total 1,000 picosecond delay when it really could have been 800. But the problem is we're not able to slice it equally. That's 200, no way to slice it right there. That's only 100, no way to include part of, you see what I mean? Yeah, so we don't want to go beyond 200. That's a 200, that's a max. That one and that one are the big slow ones along with this one. So we don't want to add even more. If somebody's already overweight, you don't say, here, eat more, give them more food. Oh, you know, they're already kiloloops, right? Let's try to put it on a diet and make it smaller. So that's the answer to that question. All right, any other comments or thoughts? Huh? Yeah. Yeah, what if the delay in the control, for example, we're calling this the decode phase, and we're saying, okay, from here to here can be done in one clock cycle. But what happens if the control part actually can't be done in one clock cycle? Then what would we do? We will slow the clock down. Yeah, exactly. So if 200 is enough for this, and enough for this, and enough for this, and enough for this, but not enough for that, then we have to back it down to 250 or 300, don't we? Yeah. I mean, so we're hoping that the control will be faster than this, or at least not slower than 200. We've got a clock time of 200. We're calling this decode. Part of decode is fetching your operands, but part of it is actually the decoding in the control units. We haven't shown that yet. That's along with your question. There's things that are not shown here. Control's not shown here, and branch and jump are not shown here. So we're just getting the main idea, and since your questions are going into specifics, I think it's time to move on. So let's move on to some specifics. Okay, now, the modifications in order to make a true pipeline architecture include you got to have control. So now, to Ur's question, look what's happening here. During the decode phase, the 6 bits at the beginning called the opcode are going to my control unit. They're saying, what instruction is it? And as you know, a whole bunch of control signals are coming out of the control unit according to the instruction. Is it R-type? Is it load? Is it jump? Is it branch? Is it store word? According to that, a bunch of signals will come out. Remember, there were 9, as I recall. Okay? Now look at those signals need to go to lots of interesting places in the data path, but not right now. The ones that are going to go here, namely ALU source and ALU op and regdest, they need to go here in the next clock cycle. Not here, where we know the value of this, but here. So we got to save them. And as you see, they're saved in the pipeline register and delivered to where they need to be. That's the meaning of this. This contains that signal, that signal, and that signal. But some of them don't need to be used in this stage. Some of them need to be used in the memory stage. So that means we have to save them and then pass them forward and save them again and then use them. And that would be the memread and the memwrite signals. Those have to be carried forward 2 more. And it looks like the branch signal as well. And then some of them actually need to be carried forward 3 clock cycles to here stored, to here stored, to here stored, and then used. And that would be the mem to reg signal to control this mux and the reg-write signal to control the write back. So some of the signals need to be delayed 1, some need to be delayed 2, some need to be delayed 3 clock cycles. None of them are used immediately. In other words, I got these signals, what am I going to do with them? The answer is nothing. They're not useful here. They're useful here 1 clock cycle later, here 2 clock cycles later, and here 3 clock cycles later. You got to save them. That's why they become part of my pipeline register as well. So I generate the controls now and save them. It's kind of like making yogurt and then instead of eating it all, putting it in the refrigerator, having some the next day, and some the next day, and some the next day. Is that okay? All right, that's the idea. So now we've added control on top of this stuff and put the control points in. Let's see if I missed anything. All control signals are determined during decode, but they're not used during decode. So they're determined during decode and then saved. Now why are they saved? Because these signals depend on this value, which is the opcode of the instruction in the decode. but 1 clock cycle later, a new instruction is going to be here. That's going to be different. These are going to be different. And if you didn't save these here, they're gone. You got to save them in a register because they're gone. When the clock comes, this moves to here. And he says, hey, get out. This is my stage now. I'm in decode. It's my opcode that we're decoding. You get out of here. So you got to be saved in the registers, or you're lost. Save it or lose it. Okay? Do we understand that idea? What's here, a clock cycle later, will be here. What's here, a clock cycle later, will be here. What's here, a clock cycle later, will be here. All right, so now let's think about this. When I decode and get these control values, I'm also getting my operand values. And now I use some of those control values on the operands to get this. And I bring the rest of them forward. Then I use some of those on those operands to get this, partially computed data, and I bring this one forward. And I use the rest of it there to get what I need and put it back in here. So the control signals travel with their cont'd data, with their Akraba Ait Olan data. As the data is processed, the control signals move along, and the ones that are needed are used to help do the activity in that stage. Do we see that? That's the key point here. Data is being processed step by step, and the controls which are associated with it are moving along and active at the right place. It's a very interesting system. Very interesting system. You might say, the people that came up with this are very clever people. I'm just explaining it. I didn't think of this. This is dahi. This is genius. This is amazing. It's very, very clever. All right, let's move on. So now we've got pipeline control. The first thing is, in the instruction fetch stage, everybody does the same thing. It doesn't matter what your instruction is. We always want to read the instruction memory. We always want to write the PC on the system clock. So there's nothing that varies according to instructions. And in the second stage, there's no optional controls there either. Everybody does the same thing in the decode stage. But after that, it starts to become different. What are you going to do in the execute stage? Well, it depends. Is the ALU going to be adding, like on load word and store word? Is it going to be subtracting, like on branch? Is it going to be doing interesting things, like on R-type? Is it going to be doing nothing, like on jump? Depends on the instruction, doesn't it? So what we've got is, look here, for R-type, the values of our control points are generated by our control unit. Yeah, we know these. We did those actually in the last lecture, but we've got to save them and use these 4 in the execute stage, use these 3 in the memory stage, and use these 2 in the write back stage. What about if it's a load word? Okay, save those and use these 4, then these 3, then those 2. How about a store word? Get all 9 of them, use 4, then 3, then 2. How about if it's a BEQ? Some don't cares, but again, same thing. Group of 4 used in the next clock cycle, group of 3 used in the clock cycle after that, group of 2 used in the clock cycle after that. Okay, that's a key idea. Can you get it? Can you wrap your head around that and get that idea? That we generate all and we save, and use a little, use a little. It's kind of like going to the bazaar and saying, I'll take 2 kilograms of apples. Are you going to go home and eat 2 kilograms of apples? Probably not. You're probably going to have some on Monday, some on Tuesday, some on Wednesday. You get them all, and then you use them as you need them. That's exactly what we're doing here. Get them all when they're available. See, if I don't go to Pazar, or in Pazar, it's gone. It goes to some other mahalla. It only comes to my neighborhood on Pazar day. Pazar is on Pazar. You got to go then and get what you want, and then you can consume it during the rest of the week. It's exactly what we've got here, only it's not apples. It's bit signals that are controlling our hardware. Anybody have any comments or questions or struggles or problems? Yeah, Buirin.
The previous question,
Yeah.
you said that if delay in the controller
Yeah. If the delay in the control, look, if the time to go in here and get these out is longer than the time to go in here and get these out, and that time is longer than the worst time, 200, we're going to have to slow our clock down. Yeah, that's a problem.
We make the data path as fast clock cycle as we cut the pieces, and we know that the same sequence will be executed the same order, fetch the data, register, whatever, and we just construct the outputs to that order. Control logic just construct the outputs for that stage.
That's what we did. This control logic is
We
constructing.
construct all the outputs and we move them.
Yeah.
We
Yeah.
just
Okay,
create
but
the needed.
okay, but yeah. Well, actually, none of them are needed. This one's needed 1 clock cycle later. This one's needed 2 clock cycles later. This one's needed 3 clock cycles later. So none of them are needed right now. They're all needed later and even later and even later.
Why do we calculate the whole?
Okay. Urkumru's question is a good one. Urkumru says, why am I making all 3 things now when I don't need them until later and even later and even later? That's his question. Why? Why make them now and save them in the refrigerator? Why not go to the bakal every day and say, I'll take 2 apples, or the manav, I'll take 2 apples, I'll take 2 apples? Why to go to Pazar on Sunday and haul back kilograms of food and then consume it slowly over the week when there's a bakal and a manav right around the corner? You just go every day. That's the analogy of your question, isn't it? Okay. The problem is this. See, the reason these control signals know themselves to be high or low or don't care is because they know what instruction is being decoded. These bits are bits 31, 30, 29, 28, 27, and 26. Do you know what those bits are, Ur? They're the opcode, exactly. The opcode for the instruction. And the opcode says how to interpret everything else and how to execute everything else. So you have to fetch it in order to get the opcode. You have to decode the opcode in order to know the control signals on the other 26 bits.
We can save the opcode.
Okay. We could save the opcode, he's right, but instead of saving the opcode, I'm saving the decoded signals which are related. These and these are exactly related. So his point is, if you save this, then you could do this in another stage. That's true. But why would I want to do decoding later when I could do decoding earlier?
We have to make 3 outputs in the same clock cycle. The 3 outputs control. What if we do
Okay.
to create one?
Okay, all right, look. If I move this control into here, then it means I both have to decode and get these 3 and use them. Right now, I just use them. So you added the decoding delay into this stage. And I think you already know, don't you, that this stage is one of the maximum stages, 200 picoseconds. We're tight for time. We don't want to slow it down. So by bringing this in, now you have an Ardashir linkage. Take the opcode which you saved, send it to the control unit, wait for that delay, out come the signals, at least these 3, and now you can do those jobs. You slowed it down by doing that.
Make a general comment. If
Okay.
one case is faster than that, instead of extending the clock cycle, we can move the control faster.
Yeah, okay. But if control is so slow that it won't fit into this length clock cycle, yeah, and it's slower than that and slower than that, and if this is the reason for our clock cycle being slower, then moving it here makes things worse instead of better. Makes it worse because now it's slow plus slow. Here it's only slow but not plus. So it actually makes things worse instead of better. Or what would you say if the control unit was so slow that it was the reason for the clock cycle? What would you say then we should do?
No, I will not talk about this architecture.
Oh, you're talking about a different architecture that's not on the board. Okay.
Some architecture, some cases faster. And
Yeah,
we
okay.
need a hard calculation.
Yeah,
We
okay.
do not need a hard calculation there, so we can
Okay.
just transport the control unit to there.
Okay.
Then the sum is maybe will be equal
All right,
to the
look.
one of the
I like the fact that he's thinking architecturally, he's thinking about performance. He's proposed a problem and now he's proposing some solutions to the problem. Talk to Radior. Okay, I'm going to have to get back on topic here in order to make progress, but I would like to answer the question that I posed you, and I'm going to pose everybody. Let's say that this is 200, and this is 100, and this is 200, and this is 200, but unfortunately this is 220. So what my clock cycle time have to be now? 220. So I slowed the whole thing down because of what you could say is the critical slow element. And so what can we do to speed that up? And there's 2 things that should come to your mind right away. What could I do about a slow control unit? Pipeline it, chop it right in the middle, okay, and make it 2 halves, first decode part and then, you know, decode the rest. Somehow, pipeline the control to make it 2 delays of 110. Then it's not the reason for the clock cycle being slow anymore. Now we're back to 200. But another very tempting option that might work, might not work, depends on the complication. A much more tempting option would be to optimize and redesign the control unit itself to try to bring it from 220 back under 200. Remember? Control unit, in theory, it can be, according to Mr. Boole, a 2-level combinational circuit. If I'm willing to spend enough gates, I can get it really fast. 2-level, and or and. So there's no problem with fast control. It's just how much money do you have in your pocket to spend on transistors. But usually, control unit will not be the slow element. Okay, and the issues, as I pointed out, would be these gigantic memories and their delay, plus the big ALU. So usually it wouldn't be, but if it is, in fact, whatever's your slow element, you can attack it and spend money to make it faster. Let's say that this is 200, and this is 200, and this is 180 and 100. So what would I love to do? I'd love to speed up these guys to get them down to 180. Is there a way to get faster memory? Is there a way to get faster memory? 200, cut off 10%, get it down to 180, speed up the clock, make the whole pipeline 10% faster. Sounds pretty nice. What do I have to do to get faster memory? Pull out your wallet and spend on higher technology, or smaller. Smaller is faster. Remember, bigger, slower, smaller is faster. Principle number 1 from CS-224. I hope you remember that. Yeah, so shrink it down a little bit. Don't hold as many instructions, as much data. It'll speed up, I promise you. You ever heard of cache? Cache memory? You know why it's faster than main memory? 2 main reasons. Smaller and faster technology. You paid more for the technology and you shrank the size and you get a faster memory. Okay, so we could make these faster if it mattered to us. All right, let's get back to where we're going. Or if you want to talk more about that, I'd be happy to, between class, after class, or in the office. All right. So now our goal is to generate these 9 signals, catch them in the pipeline register, and pass them along and use them when they're necessary. That's the whole idea here. Now we're going to start to use pictures. And this graphic symbol here is a symbol of our MIPS pipeline. It's a 5-stage pipeline. Everybody see? Instruction memory, register, ALU, data memory, rec to register. Now, interestingly enough, we only have one of these in reality, but it's shown twice. Why? Because we read from it here and we write to it here. So it's shown as if it was 2 different units. In fact, it's 1 unit, but you can read from it at the same time that you're writing to it, so it can behave as if it was 2 separate units. All right, now this diagram, we're going to use it. You're going to see very quickly and things like that. It can help us to answer questions like how many cycles does it take for execute this code? Or what's the ALU doing during cycle 4? Or if there's a hazard, why does it occur and how can it be fixed? Those are all questions that we're going to be asking. So if this diagram is useful in answering them, let's use it. All right, now here's a graphical representation of 5 instructions. Instruction 0 is followed by instruction 1, then instruction 2, then instruction 3, then instruction 4 in the code. And what we do is we show the pipeline, and then we stagger it, and we stagger it, and we stagger it, we stagger it. And so the 5 instructions are in the pipe. Right now, in clock cycle 1, 2, 3, 4, 5, look what's happening. This shows us that the register is being written with the final result from instruction 0. The data memory is being accessed by instruction number 1. The ALU is doing the job on instruction number 2's operands. We are fetching operands and decoding instruction number 3, and we're actually fetching from instruction memory instruction number 4. It shows you what everybody's doing at a given clock cycle time. That's the first thing that it shows. Okay? Once the pipeline is full, you know, it's not full here, it's not full here, it's not full here, it's not even full here. Look at that. The pipeline's not full. But now the pipeline's full. Everybody's doing something. 1 instruction is going to be completed every cycle. So therefore, 1 instruction per clock cycle is 1 cycle per instruction. So that means CPI is 1. So now I just stand here and I catch them as they come off the pipeline, and I'm getting 1 instruction, 1 fast instruction every clock cycle, or 1 instruction every fast clock cycle. Notice, though, it takes some time to fill up the pipeline. It's not filled until right here. 1 instruction in is not a full pipe, 2 is not a full pipe, 3 is not, 4 is not even a full pipeline, but 5 is. So when I fetch instruction number 4 in the 5th clock cycle, now my pipeline's full. Everybody's doing something. Notice here, only he's busy, only 2 are busy, only 3 are busy, only 4 are busy, but now all 5 are busy. So I got a full pipeline. After I fill it, then I get this incredible rate of 1 instruction per clock cycle, and it's a very fast clock cycle. Can pipelining get us into trouble? Can doing this and that huge performance gain cause any problems, cause any side effects? The answer is yes, it can. The answer is yes, it can. It can cause what are called hazards. I think the Turkish is zararlar or riskler or something like that. So there's 3 kinds. There's structural hazards, data hazards, and control hazards. We're going to talk our way through each kind of these hazards in the slides ahead. But I want to introduce the categories without going too far into the specifics right now. Structural hazards are when you try to use the same resource by 2 different instructions at the same time. That's called a structural hazard. You cannot be fetching 2 different instructions out of your instruction memory. You cannot be adding 2 things and subtracting 2 different things in the ALU at the same time. If you have 1 resource, it can do 1 thing at 1 time. If you attempt to do more than 1 thing on that resource at the same time, you have a structural hazard. Data hazards are quite different. Data hazards have to do with the data in the code and the data in the pipeline. It's an attempt to use data before it's ready. An instruction's source operands are produced by a prior instruction, which is still in the pipeline, which means it's not ready, but you still take them anyway. Well, it means you took them before they were the new value, therefore you got the old value and you should have had the new value. So it's called a data hazard. Control hazards are attempts to make a decision about a program's control flow, like on branching, before the condition has been evaluated. So I have to decide where I'm branching, or if I'm branching, but I haven't even done the subtraction yet of the 2 registers. So how can I know if I'm branching? So this happens to branch, it happens to jump instructions, it happens on exceptions. Now usually you can resolve the hazards by just waiting, just by spending some time, but that's a loss in performance. So we don't prefer to resolve our hazards just by spending time drinking tea. What we'd like to do is the pipeline control would detect the hazard and then take an action to resolve the hazard other than waiting. You can't always resolve hazards by waiting. Now let's have a look at a structural hazard. Can everybody see that if I had a single memory and I was trying to write into it here or read from it and read from it here, that I'm attempting to use the same resource at the same time for 2 different things, and that's a structural hazard. So a united memory won't work. I've got to have separate data and separate instruction memory. In that case, this is instruction memory, this is data memory, so data memory and instruction memory don't cause a conflict. But if it's just memory, a united memory, then it will cause a conflict. So you fix this with separate instruction and data memories, and that's why we're calling them IM and DM. Okay? So now with IM and DM, that's not a hazard. But now our next hazard can occur here. Look, I'm using the register file and I'm using the register file for 2 different things. For this instruction, I'm trying to write to it, and for this instruction, I'm trying to read from it. I need to fetch my source operands here. I need to write my destination data there. Isn't that a structural hazard? And the answer is yes, unless I fix it. Now, am I going to fix it by having 2 register files? I fixed the memory problem by having 2 memories, 1 for data, 1 for instruction. Do you think I can fix this by having 2 register files, 1 for writing into and a different one for reading out of? Doesn't make sense, because if I write into the writing one and then I try to read out from the reading one, it won't have the data that it's supposed to have. It has to be 1. So I can't fix it by having 2 register files. That's a nice one for memory, but it won't work for register files. So what do you think I got to do? What do you think I got to do? I got to paint one of them red and one of them green and say it's done and it's time to go home? No, not quite. All right, what I'm going to do is I'm going to change the clock timing. I'm going to cause writes to happen on the rising edge, but the pipelines will be written on the falling edge. Aha, so that means I staggered my write from the normal register loading time. So that means I write at the halfway point through a clock cycle, and that means that I'm allowed now to read out in the second half of the clock cycle, because the reading latches in to the pipeline register on the falling edge. So I split, by a timing trick, I split my read port and my write port and made them happen at different times. So technically they're not doing it at the same time anymore. They're doing it at different times, different half cycles. So therefore my hazard is resolved. And you know what else that does? That allows an interesting thing to happen. That allows me to write register 1 and put it in here and read it out here. Read from register 1 here. Oh, isn't that nice? You can put it in and get it out, or get the change in the same clock cycle that it was put in. You don't have to wait one more clock cycle because I put it in the first half and now it's available in the second half. Everybody see that? Otherwise, if it wasn't available, tell me what would happen. If this took the whole clock cycle and I only could get my data in the next one, then this would get what? The old value of R1. It would not receive that new value of R1, which is what I should receive. Instead, it would get the old value, and then just a little too late, hey, here's the new update for R1. Too late. We already read out and took the wrong value, and we added them, and now we got a bad result. You got it? In other words, this says I want that one. I want that one, not the one before that's written, but that one. So therefore, this resolves that. This resolves that. Okay, I think our time's up, so thank you for your good attention. And those of you that came to the oral exams today, I hope that was a beneficial experience. Those of you that tried to come and couldn't, I know that wasn't a very beneficial experience. We'll reschedule you for another time slot. Have a nice afternoon, everybody.